So welcome back everyone. I hope you had a refreshing break. So now we shall continue the session 2 of this day. So in this session, the topics which is going to cover is post quantum cryptography. There is industry roadmap, standards and security implications. So in this session, Dr. Priyadharshini will guide us through the latest advancements in cryptography, emerging industry standards, and the future of secure computing in the quantum era. So, dear participants, please join with me in welcoming Indra Priyadharshini once again for this highly anticipated session. So, welcome ma'am once again for this session, and the virtual dice is yours.
Okay. Now we move into one of the most impactful applications of quantum computing. We are moving into the most exciting application of quantum computing, which is quantum cryptography. So by now, even till now, we teach cryptography and network security to students. Most of the cryptographic algorithms rely on mathematical hardness. Now, let's take RSA. RSA depends on the difficulty of factoring large prime numbers. We choose a large n such that factoring that n becomes very difficult. So finding out the keys becomes difficult. Right. So even let's take elliptical cryptography. Elliptical cryptography depends on the discrete logarithmic problem. So mathematical hardness enables the security of the cryptographic algorithms. But here is the challenge. The quantum computers, there's an algorithm called Shor algorithm. He's finding as SHOR, Shor algorithm. So this algorithm is specialized in factoring large prime numbers in very less time. In polynomial time, it could find out the factorization of large prime numbers. Therefore, it is directly giving a threat to RSA algorithm. So now the question is, if the quantum computer is breaking the classical cryptography, are we going to secure the data? How are we going to secure our future? That is the biggest question in the field of cybersecurity now. How the cybersecurity algorithms should behave post quantum period. So when we search for the answer is lying in the quantum itself. So we can use quantum mechanics itself to secure the communication. So therefore, the quantum cryptography shift the security from mathematics to physics. This is the one single line summary of the entire 1 hour session now. This quantum cryptography is shifting the security from mathematics to physics. So we are going to build quantum resilient algorithms with the help of quantum mechanics. So why quantum? Uh, why do we go for quantum? For security. Because quantum computing is offering exponential speedups. As I told you, Shor algorithm is able to solve problems in polynomial time. Usually classical computers will require exponential time to solve those problems. But using quantum Shor algorithm, we can factor large prime numbers in polynomial time. Even this RSA 2048 and all, to break the RSA 2048, classical computers would take thousands of years. Companies like IBM and all, they are working for building the fault tolerant qubits. They need more number of qubits to break the RSA 2048 cipher. So they are trying to build the more number of fault tolerant qubit machines. That's that they can break. They are working towards that. Because the quantum hardware is costly, because the maintenance of quantum machines are a bit difficult, the companies like IBM are spending billions of money to build quantum multiple qubit machines. So therefore, at one point of time, they will build fault tolerant qubit machines. So we are in the phase of shifting the cryptographic algorithms that can work against quantum. That's what we are doing. So why we are looking for the quantum security itself is that because quantum is giving instant speedups. So Grover's algorithm can give quadratic speedup for such problems. It's not just speedup. Quadratic speedup it can give it. when you know how difficult it is to write a linear search, the time or amount of time required for linear search. Then what happens when we do binary search? Then what happens when we do tree search? So if we can give a speed of quadratic terms in search operations, then it would be very easy. So I mentioned two algorithms. One is Grover, which can make search very easier. The other one is Shor, which can make prime factorization easier. So therefore, the speed up that quantum computing is keeping is built on three principles: superposition, interference, and entanglement. So, so we have to note this point clearly that quantum computing is not faster for everything. It is not quick for everything. It is quick. It is powerful for certain structured problems. So that we should keep in mind. Yeah. So this we saw already in the previous lecture. So quantum is working in an entirely new model of information processing, instead of which we are going to use qubits. These qubits are represented as vectors in Hilbert space, and then computation here becomes controlled interference, which I didn't mention in the previous lecture. Interference is controlled interference. We have constructive interference, we have destructive interference. You remember we made alpha part 0 at one point and we made beta part 0 at one point. So if the answers are correct, we will strengthen them by additive interference. And then if the answers are not correct, we will cancel them by giving destructive interference. Then something called as constructive interference, instructive interference. Constructive interference is used to amplify the correct answers. Destructive interference is used to cancel the correct ones. So now the computation becomes the process of interference now. So there's an algorithm called VQE. I don't remember the expansion. QAO. QAO is the approximation. E stands for eigen. I think it is very variable quantum eigen. To find out the eigenvectors, we have an algorithm called VQE, which runs in polynomial time. It finds out eigenvectors very quickly. And then this is for approximation. You know, there are a lot of approximation problems in data such as space. We have traveling salesman problem. We have finding out the optimized route problem. That whichever problem that requires optimization, picking out the best solution from the available solutions. So such kind of problems, we can do it via QAV, that algorithm. So both of these algorithms uses entanglement. There's something called as entanglement. What is entanglement is if there are two qubits, both the qubits are so relevant to each other. Even though both the qubits are very far away from each other, you know what is a qubit, right? Qubit is it could be a combination of 0 and 1, probabilistic state in between 0 and 1. If both the qubits are very far from each other also, they are correlated. I mean, you can always derive you can always derive the probabilistic answer from one state from the other. That's called entanglement. I mean, you can think of them as a wave which is traveling together in an ocean. The waves will always go in a certain rhythm with a certain distance, certain speed. It will go, it is very uniform in between two waves. You can think of qubits like that. The entire quantum mechanics is itself nature. We derive everything from the nature. That is quantum mechanics. So far, we are doing computation, processing everything, which is very distinct from the nature. Now we are trying to move towards quantum computing and quantum mechanics, which is nothing but nature. So entanglement is nothing but the correlation between two qubits. So that is entanglement. With the help of entanglement only, this hybrid algorithms, hybrid means it is the combination of both classical and quantum. So that is where the cybersecurity or quantum cryptography is moving. There is two categories. One is quantum cryptography. Another one is post-quantum cryptography. So this quantum cryptography is totally built on quantum hardware, special hardware you need. This post-quantum cryptography is that they are just translating the available cryptographic algorithms to be quantum resilient. So that's what I'm trying to say. Yeah. this slide. Okay. So, quantum cryptography it is considered as the 21st century's cryptography. Unlike classical cryptography, the security does not rely on assumptions. We say RSA algorithm is so secure, RSA algorithm is very quick because it is very easy to compute the RSA algorithm. It doesn't involve huge mathematical operations. It's really quick, and also it's very secure because factoring large prime numbers is tough. Factoring large prime number is difficult. That's an assumption. It was assumption till quantum computing is invented. I mean, till quantum computing is so popular. Until then, we believe that factoring large prime numbers is difficult. But now it has become an assumption. So, quantum theory states that quantum cryptography is not working on assumption. Rather, it is related on physical laws. What is it? What kind of physical laws? Quantum state, probabilistic. When you measure a quantum state, you get the answer. Quantum states cannot be cloned. This is there is something called as no cloning algorithm. You can't copy one quantum state exactly as another quantum state. You can't take an arbitrary quantum state and reproduce it as similar as such. That's a very a very important concept in quantum computing. Because of this no cloning algorithm, you can't copy paste. You can't regenerate. So all these are physics. So quantum cryptography is based on this physics law. You can measure a quantum state, you can disturb a quantum state, and you can measure the output. Quantum states cannot be cloned, and then you can observe the changes in the system. You can see, you can put a quantum state in superposition and see what it is, what wave equation is generating, and then you can collapse the wave equation, and you can retrieve the output. So all this is physics. So they say they are it's not working in assumptions. Therefore, quantum is future secure. Yeah, that's what I told you. Quantum is 21st century's cryptography, and it is based on physics, not on the assumptions. So we can directly exploit physics laws to bring the advantage of information processing to quantum cryptography. Right. Okay. So this we have seen it already. We know that classical computing is deterministic. It has definite states. There is a zero state. There is a one state. When you give an input, you get an output. It is fixed. You repeat the input, say same input multiple times. You get the same output multiple times. The computations are fixed. You write a sequence of steps as program. The output is determined. You can even predetermine the output. But quantum is probabilistic. Quantum operations are probabilistic distributions. The quantum states are probabilistic. So only after measurement you will get. No, when I say measurement, you measure the superposition state. You collapse the superposition state. Only then you will get an outcome. How will you get an outcome? That is based on the probabilistic amplitudes. That is based on the value of alpha and beta. Right? So there is a superposition state. You will disturb the superposition state. You will measure the superposition state. You will collapse the superposition state. So with the help of the values of alpha and beta, you will take the outcome. So only when you measure the qubit, it will collapse into either 0 or 1. So why it is going to 0 or why it is going to 1, it depends on the value of alpha and beta. If the value of alpha is more, it will collapse to 0 state. If the value of beta is more, then it will collapse to 1 state. So this interference, this measurement, it depends on the coefficient values. And if you have more constructive interference, you will get one answer. If you have more destructive interference, you will get one answer. So all these final results are you will obtain by running the quantum circuit multiple times. Because the quantum circuits are probabilistic, because you need to measure it, you will run the quantum circuits multiple times to get the estimated probability, and you will get the outcome finally. Therefore, it is a conceptual shift. We are till then we are talking about certainty. There is a determined output. There is a determined input. Now we are moving to statistically corrected results. You run the cycles multiple times, you measure them, see the probabilities, take the outcome. Therefore, we are moving from certainty to statistically correctness. That's what we are doing. Okay. So we know this already. A classical bit is binary. A qubit exists in superposition. Right? This to these two lines explains the whole slide. A classical bit is binary. A qubit exists in superposition. You know what is superposition, right? Mathematically, it is alpha amounts of get 0 plus beta amounts of get 1. That is called as psi state. That could be the superposition of a particular qubit state. So we are storing the information in terms of amplitude probabilities. So when we take mod and square these amplitude probabilities, we will get 1 as the answer. So it can be entangled also. What is entanglement? Entanglement is there will be multiple qubits in a standard state. Each qubit is related with each other. They are correlated with each other, and then we will process the information using any quantum gate. There are a lot of quantum gates available. The important gates are C0 gate, Hadamard gate, or poly XYZ. You can use those gates. You can bring entanglement, and then you can bring out desired result, whatever you want. Therefore, one thing to be noted down here is you can store classical bits and you can process the classical bits, you can retrieve the results. Whereas qubits can be entangled, you can create correlations which classical systems cannot replicate. No, that is the important point to underline. You can produce the qubits. Qubits can be entangled. This entanglement will produce a lot of correlations between various Q states, and these correlations cannot be reproduced by a classical computer. Therefore, a hacker who is on the classical computer can never disturb your quantum secured data. That is the beauty of quantum computing. Yes. So here we are coming to the concepts, the 3 core quantum principles. So when you go and Google search quantum computing or what is quantum computing, immediately any internet source will talk about these 3 quantum principles only: superposition, entanglement, and interference. So by now you must have understood what is superposition. From the first session 1, you would have understood what is superposition, which is nothing but there exist multiple possibilities. There is no more one single 0 or single 1. There exist multiple possibilities now in between 0 and 1. So the classical bit, unlike classical bit, which is either 0 or 1, qubit could be both 0 and 1 in some linear combination. Those linear combination depends on the probabilistic amplitudes. So that is superposition. What is entanglement? If there are 2 qubits, they are very linked. They can become very linked such that one state of one qubit can determine the state of other, even if they are far apart. That is the very important point to be noted. Even if the 2 qubits are apart, from the state of qubit 1, you can determine the state of qubit 2. That is called entanglement. So this hardware gate, you can bring entanglement between qubits using hardware gate, right? So what is the use of this entanglement? If you bring entanglement among the qubits, there will be some coordination and there will be faster communication between qubits. So by which you can assume a lot of things. Take quantum key distribution. With the help of entanglement only, people will send keys. QKD is based on entanglement. So entanglement is strong non-classical correlation. That is the point to be underlined. This correlation, it cannot be reproduced by a classical computer. So there exists the security of the quantum computing. Right? The third one is the interference. Interference, okay. This we saw already. There is something called as constructive interference. There is something called as destructive interference. Quantum states can cancel each other. So we can choose the answers correctly now. If the answers are wrong, you can just discard it. If the answers are right, adding more amplitude, adding positive interference, adding constructive interference. If the answers are wrong or if it is erroneous, we will discard them by introducing destructive interference. So this is the interference is the powerful algorithm behind the Grover or the Sharp. So I mean, with these three concepts, these are called the pillars of quantum computing. We call them as superposition, entanglement, interference. So together, these three principles, the entire quantum advantage can be enabled. Right? I repeat again: superposition means multiple possibilities simultaneously. Entanglement is strong, non-classical correlation among qubits. Interference is amplification and cancellation of amplitudes. So when will we amplify if the answers are right? When will we cancel when the answers are wrong? So together we can get the quantum advantage to any algorithm. Okay. So I repeat it again. Interference, we have to note it down. We are adding the states constructively. We are removing the states destructively. So which one to cancel out, which one to get amplified? The algorithm will decide it. The gates you put on the algorithm will decide it. And then that is called as controlled interference. Using that controlled interference, we are speeding up all the algorithms. That is why Shor is able to give a quadratic speed up for search operation. That is why Gru's algorithm can work. Interference is the key behind those two algorithms. So coming back to quantum cryptography, so we are going to use the properties of quantum mechanics, quantum computing basics to secure the communication. So how does it going to help? For example, let's take the classical cryptography. What we do in classical cryptography, we will try to scramble the message. We will try to make the message in unreadable format in such a way that the attackers or intruders cannot read it. So to do that, we have a lot of algorithms, lot of ways. We will have one key to do that. We will have multiple keys to do that. Then we will search algorithms for sharing the key carefully, and then this sharing can go wrong sometimes. So you will go to something called as certificate authorities. Somebody who is in the central authority. We go there. We will up to them. We will verify that we are trusted user. We will get keys from them, and then we will start doing secure communication. All the stuff we do in classical cryptography. So all of this, why we are doing, we want our data to be secure and hidden from the intruders. In quantum computing, this is naturally quantum computing is offering us. If two persons are talking with each other, and if some disturbance in the middle, if somebody is trying to read the superposition state, for example, if Alice and Bob are talking, and somebody is trying to intrude and disturb the quantum state given by Bob, let's say. So what will happen when you disturb a quantum state? It will be collapsed to either 0 or 1. Therefore, when Bob reads the same state, Bob will get some errors. It is not the same which is intended for Bob. Therefore, if he reads if he sees the errors, he can sense something is wrong. I mean, he can sense somebody has disturbed the in between state. So that's how quantum computing will help to secure the communication. So it becomes invulnerable for the hacking attempts itself. So any unauthorized access, any interference would immediately alert the sender or receiver because of the superposition state nature. So the conventional cryptography, the classical cryptography, it relies on the key, secrecy of the key, strength of the key, how big the key is, how random the key is, how difficult for someone to guess the key, how strength the algorithm is. So the security relies on those concepts. Whereas in quantum computing, the quantum state itself is state that if somebody collapses it, it would alert the sender and receiver. That's how the sender and receiver will be in agreement. Right. Yeah. So far, what are the proofs that has been derived from the field of quantum? I've just noted down from various papers. So they have already shown that quantum computer, with a quantum computer, quantum key generation is possible. And there are certain algorithms by which this QKD can be achieved very easily with quantum. So even without full-scale quantum computers, even with classical computers, we can exchange the quantum key successfully. That is one research outcome. And then, however, some cryptographic primitives, say like perfect bit commitment or impossible in quantum settings, there are certain cryptographic primitives that cannot be replicated in quantum. That is also under research. So for all NP-complete languages, there is a zero knowledge proof existing quantum, equivalent zero knowledge proof existing quantum. So quantum teleportation means even if the qubits are apart, very distance, if the qubits are apart from each other for a very large distance, the quantum communication is possible. They say quantum teleportation and pseudo telepathy is possible in quantum computing. So all these are under research, and some of the research objectives outcomes have also been derived. Okay, let's see example of key distribution. One cryptographic process, let's see. So, like Alice is sending the quantum states. Alice is sending the quantum states. Maybe like with photon polarization, Alice is sending the quantum state. Bob is measuring it randomly. Okay, they both Alice and Bob will agree on a common base. That's yeah. Okay. Okay, right. Let me continue. Alice sends quantum states, Bob is measuring it randomly. They will have the base measurement done publicly. They will agree on the base publicly. So matching results will give us the whichever bit combination is right for them. So they will randomly change the base and they will be sending the keys. But they have already agreed on a particular base. So with that base, whichever bits they have received, only those bits they will keep for key. For other bits they will discard. This is called constructive interference and destructive interference. They are discarding some bits, they are keeping some bits based on the basis. So the set of bits that are kept for the processing, they will take that as okay. If there is a problem, if there is a base change in between them, then they will consider that as errors. And then for these errors, they will keep a threshold value. If the error value is greater than the threshold value, they will discard the entire bit stream transmission, assuming that there is a hacking attempt done in between them. So if the error rate is low, the key is secure. This is the idea. So, as I already told you, quantum computing directly threatens the RSA and elliptic curve cryptography. So, therefore, we should have a transition to post-quantum cryptography, which means we have to make the classical algorithm resistant to the quantum attacks. So, that can be done through having quantum key cryptography, quantum key distribution by enabling the quantum key distribution, we can achieve the secure communication. So, which means you know how QKD can be done and each topic can be eliminated. So, therefore, with cybersecurity must undergo a major transformation with quantum key cryptography. So, I've just listed out some applications using QAOA algorithm. I told you already, QAOA algorithm is used for choosing the optimal solutions, like choosing the best path for a traveling salesperson, choosing a particular path for graph coloring problem or the shortest routing problem, path routing problem. So complex optimization task cannot, we can go for QAOA algorithm. The slide itself shows supply chain logistics. If you're routing a courier to a particular city, which particular route you can take. For all that, we can use the QAOA algorithm. Portfolio optimization, scheduling, resource allocation, route planning, traffic management. So these are some of the applications you can use via QAOA algorithm. So quantum algorithms like QAOA attempt to find approximate solutions efficiently. So therefore, because optimization algorithms are growing in exponential space, if you apply quantum algorithms to solve approximation problems, it would be quicker. That's the idea. Another application in chemistry. So when you bring chemistry, quantum into the field of chemistry, one biggest research problem, drug discovery. Quantum computing can make the drug discovery part more achievable. So because quantum systems simulate quantum systems naturally. But I repeat again, quantum systems simulate quantum systems naturally. So this classical computer is struggling with the molecular simulation. You know, there's something called as simulation of a particle. To simulate a particle, classical computers would take years. Sometimes it is not possible to simulate a particle at all, a chemical particle at all. Therefore, with quantum computing, this particle simulation is becoming possible. Therefore, quantum algorithms like variable quantum eigenvector calculation, quantum phase estimation, all that it can easily simulate molecular energies. So, when you, if you belong to science background, you know this quantum mechanics is a framework. It's a framework or rule set of rules for testing the nature laws. To understand the nature, how nature is working, what is force, what happens when something is thrown, what happens when an elastic is pulled at both the ends, what happens when a string is tied with a stone at the end of the string. All these natural laws, you can test and study all those natural laws in the framework of quantum mechanics. So therefore, quantum mechanics is itself nature. So we are trying to bring in the concepts of quantum computing in the field of computing. So that therefore that would make the natural problems solvable. So problems like designing new machines, new medicines, creating better energy batteries, or discovering a new material, or how two molecules are interacting with each other. All those problems can be, all those use cases or problems can be easily achievable through quantum computing. That's what I'm trying to say. So again, this we have already seen. The security in quantum security is based on physics, not based on maths. Therefore, it is unbreakable. Therefore, it is we are working towards law of physics. So it is probably secure communication quantum. And this eavesdropping, somebody tries to read a state in between. It's getting automatically detected at the end of sender and receiver. Therefore, any attempt for eavesdropping is easily detected. Therefore, there's an attack called passive attack, traffic monitoring attack, eavesdropping attack. All these classical attacks, all these attacks will become obsolete in the field of quantum computing. So there is no cloning here. You can't copy an arbitrary qubit state and produce it back. Therefore, an attacker cannot duplicate the photons. The replay attack you can't do. In the field of quantum, we can't do replay attack. Replay attack is a very popular attack and it is an easy attack. And it will bring undesirable effect in between sender and receiver. So due to this no cloning nature of the quantum states, this replay attack it won't work. Therefore, it is a future proof. Measurement disturbance is unavoidable. No cloning prevents copying a quantum state. Security here, therefore, quantum security does not depend on the computational power. You can't say that the processor is very weak. My server is not having enough space. So that's why my server is prone to attacks. we need not say it in the era of quantum computing because security does not depend on the computational power. Now it is based on the physics laws and the quantum nature itself. Therefore, quantum cryptography is becoming by default secure. So it is giving us the long-term security because it is information theoretic security, not based on mathematical problems. So it is future-proof. So it enables long-term secure communication. So even infinite computing power cannot break the encryption. So therefore, the words the quantum computing research scientists use, they say past and future communication stay secure. Which means now with quantum computers coming into existence, the data in present, the data in past is under stake. So if they're going to build an entire internet with quantum, the past data and future data, both of them is going to be secure. That's why the US government, IBM is putting a lot of investments in building quantum computers, multiple qubit quantum computers, fault tolerant quantum bits. So this we have already seen it. So with the help of superposition, these key concepts, quantum is secure. Superposition, entanglement, no cloning theorem, quantum measurement is nothing but the interference. And then the QKD. Based on all this, the quantum based systems are very secure. See, if cloning is possible, see, just because it is impossible to create an exact copy of an arbitrarily unknown quantum state, the hacker cannot duplicate the qubit. Therefore, he cannot play the replay attack. If cloning is possible, let's assume if cloning is possible, we can measure quantum state multiple times. Therefore, there won't be superposition at all, right? And then there won't be, we can extract the complete information by measuring the qubits multiple times. That would break the quantum cryptography itself. That's why there is no cloning. We cannot able to create an exact copy of an unknown qubit state. So we can't duplicate the qubit. The nature itself preventing this. Therefore, the quantum computing systems are secure by default. So, quantum cryptography. I told you already, quantum cryptography requires special hardware. You need a quantum computing machine. You need photons with physics knowledge to generate quantum cryptography algorithms. Post quantum cryptography is that it is mathematical. We are just extending the classical cryptographic algorithms to be quantum resilient, to be quantum resistant, right? So that is called as post quantum cryptography. So both of them, both quantum cryptography and post quantum cryptography is going to coexist in future. So there will be a lot of hybrid algorithms coming in future. If you are a researcher or if you are doing PhD, if you pick up a research problem based on quantum computing and cryptography together, then you have a lot of research scope. Because in future there is going to be hybrid algorithms. So I'm not saying that quantum computers are going to replace classical computers. It's not surely. It's not that particular statement. I'm just saying to build the security, there is going to be a lot of mixture of classical and quantum cryptographic algorithms coming into existence to safeguard the internet. So QKD. So QKD is securely sharing the key, distributing the encryption keys among the sender and receiver who's involved in quantum computing. So the QKD will not encrypt the message; it's just share the key. So it is going to be a shared key exchange. Therefore, anybody who disturbs the transmission in the middle, they get easily notified. So any interrupts, any disturbance in the quantum state, it is very detectable. Therefore, the sender and receiver would know that. So this is one popular protocol for changing the keys among the sender and receiver. So it is the first algorithm proposed for quantum key distribution. So let's say Alice is said how this protocol works is Alice will send photons in random polarizations, which means Alice is sending set of qubits. Okay, Bob will measure randomly, and then they will compare the base publicly. If the bases are matching, only those bits they will retrieve, and those retrieved bits will form the key. The other error bits they will discard it. Therefore, at the end, the matching base bits will form the original key. That's how the BP84 protocol works. I think I have a diagram. Yeah. You can see here, Alice is sending us a sequence of bits, and then this is the Bob's base. Bob is just choosing random bases. Only when the base is matched with Alice's base, that bit get measured. That measured bit he will keep it as the key. If the base is not matching between Alice and Bob, that bit the Bob will discard. So only the base is matching bits are procured, and that will form the original key. So any qubit will have two bases. Either it is going to be a horizontal basis, or it could be a vertical basis, or they can go for diagonal reductive basis. But in any way, the basis of Alice and Bob will match. So only matched bits will they will keep it, and the matching bits they will keep it as key. Once they agree on a key, and then they'll start communicating. Then just like a AES algorithm or a DES algorithm, some random classical algorithm they can put, and they can start communicating. If suppose, let's say somebody is intruding, let's say Eve is intruding, right? So Alice has sent the photons. So she has chosen two different pieces, and then she has encoded the photons, and she has sent the bit streams. So Bob will measure each photon using random interface bases. So only for the matching base, Bob will retrieve the bits and he will keep it. Okay. So if suppose if some intruder has measured the quantum state, the base would not match, and when Bob is measuring the bit, Bob would generate an error. So if there is an error, and if the error is a very small subset, then the Bob will ignore it. If the error threshold is more, then Bob will understand that there is an intruder, somebody is trying to measure the quantum state in between. So he will discard the entire key, and they will again start the key sharing. If there is a low error rate, they will keep the rest as the key, and they will start communicating. So this is how quantum key distribution works. There is one more protocol called E91 protocol. So this is how Eve. So if Eve has measured the photons, she would have collapsed the state. If she has collapsed the state, then the measurement would have changed the polarization. If that polarization has changed, then errors would have gotten introduced. If there are errors, Bob would measure it wrongly. If Bob is measuring wrongly, then he will increase the error threshold. If the error threshold is increased, he will discard the key. So this is how security is unconditionally guaranteed. Right? So there is one more protocol called E91 protocol. This is based on the entanglement. So here they will, Alice and Bob will measure the entangled qubits. You know what is entangled qubits? They are related to each other. If the entanglement, that correlation is not reproduced correctly, they will discard it. Otherwise, they'll keep that as the key. So now this algorithm is based on the Bell's state, the entanglement and Bell's state. So as I already told you, there are some simulation platforms for testing the quantum cryptography in quantums. There are safe environments to test our protocols. You can see the behavior of the quantum states. You can visualize the qubits, etc. So I've just listed out it. I have only used IBM Qiskit on this. There's a platform called Qtip toolbox in Python, via which you can replicate the quantum algorithms. You can see the state evolution. You can visualize the qubits and see. You can produce the entanglement effect and interference effect also. Qiskit we can use gates. We can use Harman gates. We can use poly-X gate, poly-Z gate, T-gate to construct the quantum circuit, and then we can try to give the get-wise inputs, and you can see the interferences and outputs, etc. So IBM has a open source quantum SDK. and then Python-based circuit design it has. So it even has the BB84 algorithm protocol, E91 protocol for key distribution also. So we can you can see the demos. There are a lot of videos also available in IBM's platform. You can just click and play the video, understand it, and then you can try to reproduce it. There is something called as Quantum Inspire. It is a web-based simulator. So we can say we can it is a it works in the internet. You need not even install it. You can use that to produce the entanglement effect. We can see the QKD demos, etc. So Quantum Inspire and then Qt Qiskit, three simulation tools for quantum testing and deployment. Okay, I have just I took all this from internet only. What is happening in the real world in the quantum? So China has launched a quantum satellite. They tried to do entanglement distribution in very large distance. That is an open research problem in quantum. If the qubits are very far away from each other, the communication is prone to errors. And qubits is also prone to errors because it is based on superposition probability. There are a lot of errors. So quantum error correction and then the distance between qubits. Those two are open research problems. So government and defense, US government and defense, they are working in secure sensor networks for the private communication. They're trying to build a private communication network using quantum, such that it would prevent spoofing and data leaks. And then they are trying to invest on a lot of IoT security and use it for a military defense purpose. And two more case studies I took. Yeah. These are the open research problems I was talking about. So, the key distribution or even quantum communication, which are far apart from each other, is very prone to errors. So that is a research problem. How to make two quantum nodes communicate with each other, or how to make two qubits talk with each other, even though they are very far apart. But these two qubits are having all the nature's law. They have entanglement, they have superposition, etc. But the communication is prone to errors. How to avoid that? And then how to build quantum resistant algorithms and integrate them with the classical infrastructure. Because quantum hardwares are very costly and it is not easy to maintain a quantum machine and build a quantum machine. We have to work with the classical architecture, similar in quantum algorithms. So how to integrate the quantum simulation algorithm with classical hardware? That is one research problem. And then only standards is getting there are standardization bodies like NIST, ISO, all those standardization bodies are working towards the quantum computing standards. So standardization and certification. In that also there are I could say there are a lot of research papers that are only review papers that is that talks about standardization for quantum computing. And then quantum safe cryptographic agility. I mean the continuous process of building quantum safe cryptographic algorithms. There's a popular saying now the security is not a separate phase in product development. Security is built in the design itself. Even before the actual development of product starts, during the design itself, people are integrating the security part. The same goes with the quantum part. So when you are working towards a security algorithm or a cryptographic algorithm, you should think in terms of quantum only. There is no more classical cryptographic algorithm. Either it should be a quantum cryptographic algorithm or it should be a hybrid classical quantum cryptographic algorithm. So all these are open research problems with respect to quantum computing. Okay. This also I talked about. The challenge is in deploying the quantum. Quantum networks are expensive. Also, scaling quantum is difficult. You build a circuit, you run it, test it, you want to add some more nodes, then that becomes a difficult part. You have to rework it again. Entire reworking. It's not like classical computer algorithms, where we build a network, we build a circuit, and then you can increase the number of nodes, increase the packet size, test it. All that we can easily do in classical computing scenario. But in quantum computing, scaling is a very big headache. Um, Even for the small testing and deployment purpose, we used to rework the entire quantum circuit. That becomes a problem. But now the research is progressing rapidly, such that when we see research papers, we get a lot of new ideas, new ways of solving the problem is coming into existence. These are the deployment challenges. Okay, so this post-quantum cryptography, how to change the classical algorithm resistant to quantum attacks. So far, when we talk about quantum cryptography, it is full of simulations only. Now, most of us would not have worked with the actual quantum computer. We build simulated quantum computer circuits, simulated quantum computing environment in IBM Qiskit or something like that, and then we test and deploy it, right? So when it comes to when it comes to post-quantum cryptography, also we are going to extend the classical algorithm that can defend against the quantum attacks. So I can see a lot of research papers in lattice-based cryptography, code-based cryptography, hash-based signatures. All these kind of cryptographic algorithms, they are trying to embed the quantum computing features into it, such that those algorithms will stand against quantum attacks. Those research works I have seen in the post-quantum cryptography section. Otherwise, when you go and see the research papers, most of the research papers would have talked about how to break the RSA, how to break the ECC with quantum computing. There are a lot of research papers on that. But to make a classical cryptographic algorithm resistant to quantum attacks, I could see very few papers, and those papers are based on lattice-based cryptography, code-based cryptography, and hash-based signatures. Okay, so why do we need post-quantum cryptography, which we have already discussed? Quantum computers, at least in theory, can break RSA. Why in theory? Because the 2048-bit RSA, to break the 2048-bit RSA, they need more number of fault-tolerant qubits. You have to note down the term fault-tolerant. There are machines with multiple qubits, but fault-tolerant qubits is still another construction. IBM is working on that. So they have the small prime factorization. They have already demonstrated. They can break the RSA algorithm to certain extent. 2048-bit RSA, they are trying to break it. So when they are investing in breaking the RSA or ACC or defeat element, they are thinking that now we don't have the required quantum computing hardware. Maybe in future, maybe say to 1 decade or 2 decades, they would have the required amount of quantum computing hardware. In that case, they are thinking now take the data, take all the data, keep it with you. Once the hardware is ready, you can decrypt it later. That's how quantum computing research scientists are thinking. So that's called harvest now, decrypt later. So take all the data, record it today, and keep it. Once the quantum machine hardware is ready, we can decrypt it. That's what the attackers who uses quantum computing thinks. So we need to have quantum safe algorithms now itself. Now itself, sure algorithm can factor large numbers in polynomial time. Therefore, RSA is in stake. Therefore, over time, the hardware is becoming quantum hardware is becoming accessible. If it gets accessible, then a lot of research will come on that part also. So there are two branches of people working it. One who is trying to bring the classical cryptography using quantum. One who is trying to extend the classical cryptography to put it in very simple analogy, classical encryption is like putting the valuable things, locking it inside the door. That is classical encryption. Keep the valuable things, shut the door, lock it. Quantum computers are giving a duplicate key to the hackers, right? So therefore, post-quantum cryptography will change the door into an unpredictable or a tough maze in such a way that even with quantum computing key, nobody can enter. I repeat it. A classical encryption is like putting all the valuable things inside a room, locking it with a key. So you lock it and you go walk away with a key. Quantum computing guys will give the duplicate key to the hacker. So now, if the world is not ready with post-quantum cryptography, what post-quantum quantum cryptography would do, along with the door, it will replace the door with some difficult puzzle-based maze in such a way that even with quantum computing key, the intruder cannot enter. So post-quantum cryptography should replace the door. Therefore, it should replace the classical algorithm with quantum-based hybrid algorithm that can defend the attacks. That is the entire summary of the so far whatever I'm talking. Okay, so I have listed out. I told you I have seen some research papers for which the quantum resilient solutions have returned. So there is a lattice based cryptography which can solve shortest window problem, learning with errors problem, etc. So such kind of problem is assumed to be hard even in the quantum computer. And there is code-based cryptography. The mathematical thing is the mathematical concept behind the code-based cryptography is random linear codes. And then multivariate polynomial cryptography. Yeah. Multivariate polynomial cryptography that uses multivariate polynomial equations. So these three slides, these three classical cryptography algorithms that is assumed to be hard even in the presence of a quantum computer. Okay, hash-based cryptography, which is the strength is behind the collisions of hash functions, and then the computing the isogenes between elliptic curves, finding a map between elliptic curves. So all the 1, 2, and then these three. These three classical cryptography algorithms, the mathematics behind them is difficult for a quantum computer to break it. That is what I'm trying to tell you. Oh, okay. So that's it for the day. I think I have covered whatever I want to tell you. To complete it, to put the summary on whatever I've talked, quantum computing represents both disruption and opportunity. I mean, it is breaking and also it is giving opportunity to work against the breaking. So it is threatening the current security system, but it is also enabling us to fundamentally secure the communication. So the future will involve a hybrid approach, combining the quantum cryptography and post-quantum cryptography. So, I mean, people have already started doing research. There are possible outcomes. The transition has already begun. So, people who are in the idea of pursuing research or doing research can pick up a problem based on this hybrid algorithms, combination of classical and quantum cryptography. So even the governments, technology companies are actively planning the transition to quantum safe communication. There are roadmaps deploying quantum key distribution networks, developing post quantum cryptography solutions, building hybrid systems, all that. You take telecom, you take finance, you take banking, all of them are working. You can see there are a lot of white papers. If you go and search instead of research papers, industry white papers are available for this post quantum cryptography. I could see a lot of white papers. So go for standardization, like there is a standards like for those for researchers, this might be useful. There's something called as this. Most of us would have know NIST, and then there is something called as ETSI. I don't remember the expansion. NIST, all of us would have known National Institute of Standards and Technology, ETSI, and then ISO. All these are, there are a lot of research papers for studying about quantum standardizations. So NIST, they have selected already lattice lattice-based and hash-based algorithms for post-quantum standardization. So we should all of us should be worried about this problem. Harvest now, decrypt later. You know that this particular line. We should all of as a computer science engineers, we should worry about this part. Harvest now, decrypt later. This threat can only be defined type of post-quantum cryptography. So now itself, big IT giants have started transitioning towards quantum safe cryptographic system to ensure long-term data security. So therefore, as a researcher, as a part of academia, engineering academia, we should start learning the combination of classical plus quantum cryptographic algorithms, particularly if we belong to cybersecurity. So that's it for today. I've completed 10 minutes earlier. If there are any queries, I could take up.
Thank you, Dr. Indra. Thank you. We now welcome the questions from the participants. Dear participants, please post them in the chat box, or you can unmute and directly you can interact with Dr. Indra. Dear participants, any queries from the session 1 or session 2? We have a very eminent person with us. Let's take more insights from her in such an exciting field. We have many research scholars also in our meet, ma'am. Even we have industry people connected with us.
Oh, there are questions in chat, I guess.
No queries from Samuel Dinesh. Vidya Prakash, Rajendran sir has given thank you. Participants, please unmute your audio and you can have any questions. Ma'am is there with us. Participants, the feedback form for the day 4, session 1 and session 2 is posted in the chat box. I repeat, the day 4 today, session 1 and 2, the feedback is posted on the chat box. It will be live for the next 10 to 15 minutes only. You can give your suggestions, your feedback regarding the sessions and much more suggestions awaited for the upcoming programs planned from our Department of Computer Science and Engineering from RMK CET. It was a very clear explanation, ma'am. Any queries? Dr. Indra, I have a question.
Yes, ma'am.
This related papers or courses do you have at VIT, and could you suggest some teaching pedagogies in case if you have this course at your campus?
We are yet to start the UG course, BTech quantum computing. But we have a value-added course, quantum computing, running right now in the campus. Maybe
Okay.
for the next semester, again, we'll start. That time, I'll keep you posted, ma'am.
Oh, sure, ma'am, sure.
But
Because
it is
it's
open for students. I don't, for faculties, if there are any courses available, I'll let you know. But I could tell you there is a NPTEL course offered by IB and I Kharagpur together,
okay.
especially for quantum computing. That we can take up now. So, I took that course before I started delving into quantum computing. It is really a very nice course. This is one way. The second one is we can go to IBM platform, IBM Qiskit platform, watch their videos and use their platform to test it.
Okay. Thank you, ma'am. Thank you. Any specific courses? There's a question from Madam Krishna about the courses. Any specific courses related to quantum computing that would help us get enhance ourselves in this new field of computing?
Okay. The IIT Kharagpur and IBM together is offering an NPTEL course. And recently, I don't remember the FDP conducted by some NIT, ma'am. I don't remember which NIT it is. I
Okay,
could
ma'am.
do one thing. I will take the YouTube video links from that particular FDP and I will share it to.
Yeah, ma'am. Sure, ma'am. Sure. Thank you. That would help us a lot, ma'am.
I will do that.
Yeah, thank you. Thank you so much, ma'am. And even in the value-added course, do you have any specific pedagogies that you follow to make students the course interesting? Could you suggest anything?
Quantum mechanics, we are starting with mathematical foundations. Quantum mechanics only.
Mechanics. Okay, ma'am. Okay.
It's actually a 30-hour course. So every Saturday the course is conducted. Every Saturday the course is conducted. It will go to 5 Saturdays. So one
Okay.
Saturday quantum mechanics will start, and then we'll start slowly start introducing to quantum computing. And then finally, they are given a project on IBM Qiskit platform.
So they directly do the projects there.
Yes, yes, ma'am.
Yeah, okay, ma'am. Okay, fine. Thank you. Thank you. Any other doubts? Any queries? Any clarifications needed from Dr. Indra? You can post it. Again, there is a question. Can you repeat again the courses?
Okay. Put it in the chat.
Yeah, ma'am. That would be more better. Participants, you can please look into the chat box. Yes. I think everybody could see the courses related. The madam is posted in the chat box. The course is NPTEL course offered by IIT and IBM on quantum computing fundamentals. And also there are platform videos available in IBM. Thank you, ma'am. Thank you.
Can't trust your AI results? Let Borium sift through 170 million papers and find verified answers.
I was searching for the quantum that particular. I couldn't find out. I'll take that and I'll share it later.
Ma'am, your audio is very less.
Yeah. I was searching for that.
Okay, ma'am. Okay, fine. Okay, ma'am. Okay.
And then later I'll share it to Dr.
Yeah. Yeah, sure, ma'am. Sure, ma'am. Any other queries? Dear participants, the feedback link is posted on the chat box. Anto, sir?
Yes.
Shall we conclude?
Yeah, yes, ma'am.
Thank you, Dr. Indra Priyadharshini. It was an incredibly insightful session on the post-quantum cryptography, dealing with the industry roadmap, standards, and security implications. Thank you so much. So with this, we conclude our day 4 of our 6-day International Faculty Development Program. On behalf of the organizing team in the Department of Computer Science and Engineering, RMK CET, we extend our heartfelt gratitude to Dr. Indra for her exceptionally insightful sessions on both quantum computing fundamentals and post-quantum cryptography. Her expertise, her clarity, and the practical perspectives truly enriched our understanding, and it has inspired us to explore more on these cutting-edge technologies in research, in teaching, and real-world applications. We also thank all the participants for your engagement, your questions, and enthusiasm in today's sessions. And your involvement is what makes actually our FDP very collaborative and enriching experience. We have crossed 4 days with the different sessions. And this day 4 has given us a deep understanding of the next generation computing and also the security paradigms. So we hope these learnings will spark new ideas and initiatives in our academic and professional journeys. Looking forward to welcome you all to the day 5 tomorrow, where we will be dwelling into the real world industry applications, the cutting edge solution, and we have opportunities for collaborative research. A heartfelt thanks to Dr. Indra, all the enthusiastic participants, and the CSC team at RMK CET for making this day a remarkable success. Thank you so much. See you then. Till then, bye. Thank you, ma'am. Thank you. Thank you, ma'am. Thank you all.